Welcome again to this presentation where we are discussing the question and the answers regarding thermochemistry. Last time we ended on question 37. Today we are starting on question 38. Question 38 is asking what is an isothermal process, what is the change in internal energy for isothermal process. That's the first sub-question. The second sub-question is asking, explain the following thermodynamic process: isobaric expansion, isobaric compression, isochoric, adiabatic expansion, adiabatic compression. It is also asking, show that the change in internal energy in the mentioned processes is equal to nCvdT. Let's quickly see the answer for this question. We need to start on the isothermal process, and they're asking what is an isothermal process and what is internal energy for isothermal process. Let's see, for example, if you are taking a thermodynamic process in which the temperature of a system remains constant, and that system, that is what you call a thermodynamic process. A thermodynamic process is a process in which the temperature of the system remains constant. An example is a refrigerator. The refrigerator works isothermally. The heat energy is removed and transmitted to the surrounding environment. For the refrigerator, we have the heat energy which is removed and transmitted to the surrounding environment. Another example is the heat pump. The heat is either removed or the heat is brought in the house. So when you are using the heat pump to heat the house, then the heat is either removed or it is brought inside the house so that the temperature of the house remains constant. Isothermal process is a process in which the temperature of the system remains constant. If you can check on this diagram, during an isothermal process, the temperature remains constant while the pressure and the volume are changing. For example, you can see the pressure is decreasing while the volume is increasing. You can see the volume increasing while the pressure is decreasing. If we can then construct a temperature and volume diagram, you can see that the isothermal process is a process in which the temperature of the system remains constant. You can see that here the temperature remains constant. From A to B, the temperature remains constant. From B to A also, the temperature remains constant. But check, from A to B, the temperature remains constant, but the volume is increasing. So from here, from A to B, we are increasing the volume, and from B to A, we are decreasing the volume. The thermodynamic process is a process in which the temperature remains constant while the volume and the pressure are changing. Now let's see what is an isothermal expansion. That means we are expanding the gas. If you can see, for example, this diagram, we have an external thermal reservoirs and you have a gas which is expanding because it is an isothermal expansion, but the gas has to expand at constant volume, at constant temperature, not at constant volume, because you have isothermal expansion. Isothermal expansion, that means the gas has to expand at a constant temperature, but the pressure and the volume they are changing. That means because it is an expansion, the volume is going to increase and the pressure is going to decrease because we are having isothermal expansion. Constant temperature, the volume and the pressure, they are changing. If it is expansion, that means the volume is increasing while the pressure is decreasing. Now, if the volume is increasing and the pressure is decreasing, that means the temperature also has to change. temperature has to decrease. Then that is the reason why we are putting external thermal reservoirs so that the temperature can be constant. This external thermal reservoirs is to make sure that the temperature is compensated. There is a contact between the external thermal reservoirs and the system in which there is a heat exchange. So as you have said, the thermodynamic process is a process in which the temperature remains constant. That is the basis for the isothermal process. Whether it is isothermal expansion or whether it is isothermal compression, the temperature should remain constant. During isothermal expansion, the gas does work. That means if the gas does work, the work done is negative. Then the volume is going to increase, the pressure is going to decrease, but the temperature, as we have said, should remain constant. So the pressure and the volume, they are changing, and the temperature is going to remain constant. The volume is going to increase during isothermal expansion, while the pressure is decreasing. Again, we have said that the system must absorb heat so that in order to conserve the temperature, there is a heat exchange. So these external thermal reservoirs exchange the heat with the system so that the temperature remains constant. So the system is in contact with a thermal reservoirs from outside. There is heat exchange so that the temperature can be conserved. Now, what is the internal energy for a night gas when there is an isothermal expansion? Here, because we have the constant temperature, we know that the internal energy is a function of temperature. Internal energy is a function of temperature. If the temperature is not changing, that means the internal energy is also equal to 0. So here there is no change in the temperature. So the change in internal energy is 0. So we have the change in internal energy is equal to 0. So we know that the change in internal energy is equal to the change in the heat plus the change in the work done. Then in that case, if this is 0, the change in internal energy is 0, that means delta Q is equal to minus delta W. So here we will ask to determine the internal energy for an isothermal process. So now we have seen that for an isothermal expansion, the internal energy is equal to 0 because the temperature is constant and the internal energy is in function of temperature. Let's look for isothermal compression. During isothermal compression, now the gas is compressed. It is a compression of the gas. So that means the volume is going to decrease. Here, the volume is going to decrease, the pressure is going to increase, but the temperature should remain constant. Now, we should have an external cold reservoirs to exchange so that this heat, which is produced when there is a compression, the heat which is increasing here, there is external reservoirs in which it is going to exchange with the cold reservoirs so that temperature remains constant. Because here, a compression, you are increasing the pressure, you are increasing the temperature. Then for isothermal compression, to get the constant temperature, you should have the external cold reservoir so that the pressure, the extent, the heat which is produced here is exchanged with the external cold reservoir so that the temperature here remains constant. So there is an exchange of heat between the system with the external cold reservoirs so that the temperature remains constant because isothermal is a constant temperature system. So we have seen that thermodynamic process in which is a process in which the temperature remains constant. During isothermal compression, when you have isothermal compression, the gas is compressed. So the gas is compressed, we are compressing the gas. The volume decreases. You can see if you compress the gas, the volume decreases. The pressure increases. So we are increasing the pressure. And the temperature should remain constant. And for the temperature to remain constant, we should be having these external cold reservoirs. so that there is an exchange of the heat to the external cold reservoirs to maintain the temperature. The system here must lose heat. It's losing heat in order to conserve the temperature. That means the heat here must be lost and sent to the external cold reservoirs so that the temperature remains constant. The temperature in isothermal compression or isothermal expansion here remain constant. So that means here a system is in contact with outside cold reservoirs so that the heat inside is exchanged with the external cold reservoirs to make sure that the temperature is constant. So here also the internal energy is in function of temperature. Internal energy is in function of the temperature. That means if the temperature remains constant, the internal energy is automatically zero. There is no change in temperature because we have isothermal process. So the change in internal energy is zero. Then here we have 0 is equal to dW plus dQ. That means dQ is equal minus dW. So that was the first sub-question of our question. Now we need to move to the second sub-question where we need to explain different process. We need to start with isobaric process. What is an isobaric process? An isobaric process is a process taking place at the constant pressure. Here, isobaric process, we have constant pressure. The constant pressure is obtained when the volume is expanded or contracted. Here also we have an expansion and compression, but it should expand and compress at constant pressure. An example of isobaric process is the boiling water. When you are boiling water to steam, you are changing water to steam, and here the pressure remains constant. Or if you are freezing the water to ice, that is also an example of the isobaric process. Another isobaric process is the pressure cooker. When we have a pressure cooker, so that we are using to cook the rice at our home, when you are using the pressure cooker also is an isobaric process where the pressure remains constant. When there is an increase of the pressure, the pressure cooker is starting to twisting so that the excess pressure is released and come to its desired pressure. So that means the excess pressure is released. You can see if you are cooking, when the pressure is increasing, there is a release of the excess pressure so that the pressure remains constant inside the pressure cooker. So here we have a diagram. So for isobaric process, the pressure should remain constant. From A to B, the pressure remains constant. That is isobaric process. But the volume is changing. The pressure remains constant from A to B, while the volume is increasing. When we are drawing the TV diagram, that means here what is remaining constant here is this curve is for the pressure. The pressure remains constant, while the temperature and the volume are increasing. You can see the temperature is increasing and the volume is increasing, and the pressure remains constant. If you can see, for example, this diagram, so here we are compressing and expanding the gas, and you can see that we have the change in the temperature and the change in the volume. If you are compressing the gas, the temperature is decreasing, the volume also is decreasing, and if you are expanding the gas, the temperature increases and the volume increases. So if you can also see another diagram, you can see here the pressure for isobaric process, the pressure remains constant. The pressure remains constant while the volume is increasing. So we have the starting, then A to B, the initial state, then the volume is increasing from VA to VB. So during the isobaric process, we have a constant pressure and we have the volume which is increasing. Let's see in isobaric expansion, that means the gas here is going to expand against the constant pressure. This is an expansion, at a constant pressure. So as we know, pressure is proportional. This is the pressure is proportional to the frequency at which the molecules collide with this piston. That means the molecule colliding the piston, the pressure is proportional to the frequency at which the molecule are colliding with the piston, and also is also proportional to the speed. So now when you are expanding, you are now increasing the distance in which the molecules has to travel, and the collision frequency also is going to decrease. So that means here that the pressure is going to decrease. So how then do we do so that the pressure stay constant? Then here we need to add also the external reservoirs to supply the heat, so that the molecules they can be accelerated to compensate with the pressure also during the expansion. An expansion of gas would cause the pressure and temperature to decrease. When you are expanding the gas, the pressure and temperature to decrease, and to get an isobaric process or to counteract this and keep the pressure constant, you need to add heat to an expansion of gas. So here we need to put the external hot reservoirs, so that we supply the heat to the system to compensate, so that we can have the constant pressure. So how do you determine then, how do you show that for an isobaric expansion, the internal energy is equal to nCvdT? So here we have said that the heat is added. We are adding the heat. That means delta Q is positive because we are adding the heat. When we are talking positive and negative, that is the conversion. So here, for people in physics, they are using the different sign, but in chemistry, when we add the heat, we are using the positive sign. When the heat is removed, we use the negative sign. When the gas expands, we use the negative sign, and when the gas is compressed, we use positive sign. So when you see that, when you are a physics, you will see that there is different terminology that we use in different signs depending on the chemistry and physics. So when you are a physics student, then you will know that the signs are different in what we are using here, because here we are dealing with the chemistry signs. So here we have the gas which is expanding, and the delta W, the work done, is equal to negative. Then we know that delta U, the internal energy, is equal to dQ plus dW, and we know that du will be equal to dQ, because the dQ will be positive, the heat will be added to the system, and dW it will be negative. So now here, how dW is it going to be negative? So here we need to know that if you are changing dV, if dV here it will be positive, the pressure also is positive. That means that for us to get the dW which is negative, we have to press this sign which is minus. So remember, the work done is equal to negative P dV. So here then, if we have the work done which is equal to negative P dV, here automatically you get the negative work done, because here dV is positive, the volume is increasing. That means the final volume is higher than the initial volume. The pressure is constant, so that means that the heat, the delta Q, is equal to nCvdT. Here we are using the heat capacity at constant pressure, because the pressure is constant. If you can replace then this dQ, we know that du is equal to dQ minus P dV. That means du is equal to nCvdT. We are replacing this one to this term delta Q minus P dV. So we know that P dV is equal to nRdt. That means then you can replace this P dV by nRdt. The PV is equal to nRT. So here we have du is equal to nCvdT. This is the term nCvdT minus nRT. Then we can put delta U is equal to n delta T Cp minus R. So remember, we have shown the relationship between Cp minus Cv is equal to R. So remember, the relationship between Cp and Cv is that Cp minus Cv is equal to R. Then you can get Cv is equal to Cp minus R. That means this Cp minus R is Cv. We can get then the internal energy is equal to nDT Cv. So internal energy then for an isobaric process is equal to nCvdT, because the question was asking to explain isobaric expansion, isobaric compression, and also to show that for isobaric process, isobaric expansion, and the isobaric compression, the internal energy is equal to nCvdT. Now let's go to isobaric compression. Here we are compressing the gas. That means the volume is going to decrease. Here we need to move from B to A by decreasing the volume, but it has to be at constant pressure. So B to A, we are decreasing the volume, but at constant pressure. So compression of gas would cause the pressure and temperature to increase. When you are compressing the gas, that means the pressure and the temperature are going to increase. You are compressing the gas, you are increasing the pressure, you are also increasing the temperature. And because it is an isobaric process, you want the pressure to stay constant. So then to keep the pressure constant, what do we need? You need to remove the heat from the system so that the pressure stays constant. So removing the heat, that means you need to add an external cold reservoirs. So that means isobaric compression is a cooling process. We are removing the heat from the system, while an isobaric expansion is a heating process. We are adding heat to the system. Now here, to show that the internal energy is equal to nCvdT, we are going to use the same formula. And we know that D is equal to dQ plus dW. So I told you that you have a cooling process. That means heat is removed. So the heat is negative because the heat is removed from the system. So here the gas is compressed. I told you that dW is positive when you have the gas which is compressed. So then when you are replacing dQ is equal to NCP T2 minus T1. So because here we are removing the heat, that means here T2 will be less than T1 because we are removing the heat. That means automatically here we have the negative sign because T2 minus T1 will be negative because we are removing the heat. That means T2 will be less than T1. Then here we press the C minus P dV because the work done is positive. How the work done is positive? Remember, V2 minus V1, here the volume is decreasing. So that means here we have a negative because we are decreasing the volume. So that means V2 is less than V1. So here we have a negative sign. For us to get dW, which is positive, we need to press the negative sign here. So minus P dV. So then here we replace, we know that this is the NCP, this is dt minus NR dt because we know PV is equal to NR dt. Then you have N dt, Cp minus L, and we know that Cp minus L is equal to Cv. So here we have the D is equal to N dt Cv. So nCv dt. That means also the internal energy for isobaric compression is equal to nCv dt. So internal energy for isobaric processes is equal to nCv dt. So let's see another process which is isochoric process. That means it is a thermodynamic process taking place at the constant volume. If a process is taking place at constant volume, in that case we call it an isochoric process. So sometimes it is also called isometric process or constant volume process. An example is when we are burning the gasoline air mixture. You have the gasoline and air mixture in a car engine, and you have here a constant volume. There is an increase in the temperature and the pressure when you are burning the gasoline. So the gas, so that means the gas inside the engine is going to have the high pressure and temperature, while the volume remain constant. So the meanwhile the volume of the gas remain exactly the same. The volume has to remain constant so to have a isochoric process. So we have here the volume which is remaining constant. The volume remaining constant. The volume is constant while the pressure is increasing. So we have here then the pressure and the temperature. So they are increasing while the volume remains constant. We have the pressure, the temperature, they are increasing, and the volume remains constant in the isochoric process. So here we have the pressure is increasing, the volume remains constant. So isochoric process occurs at constant volume. If it is occurring at constant volume, remember work done is equal negative PDV, and the volume, now the change in volume is equal to 0. That means the work done is 0 in isochoric process. When the process is happening at constant volume, that means the work done is 0 because delta V is equal to 0. So now, how do you show that this process, the internal energy for this process is equal to nCvdT? Remember, we have D is equal to dQ plus C dW, and then the work done is 0. So we have a constant volume, and this work done is 0. That means D is equal to dQ. But it's happening, it's dQ, but at constant volume. So we have a constant volume, that means dQ is equal to nCvdT. Here we need to use the heat capacity constant volume. That means du is equal to dQ is equal to nCvdT. That means then here also we are having the du internal energy is equal to nCvdT. So isobaric process internal energy is equal to nCvdT. Isochoric process internal energy is equal to nCvdT. And the isothermal process, so far you have seen that the internal energy is equal to 0 for isothermal process. What is the next process is what you call adiabatic process. So adiabatic process is a process where there is no exchange of heat from the system to its surrounding. Here, there is no exchange of heat. We have seen that for other process, when we are considering other process, we have seen that there is an external reservoirs to compensate the heat. So here, then, if you want to maintain the temperature and you want to constant temperature and you want to maintain constant pressure, we have seen that we have external reservoirs to exchange so that the temperature is constant or the pressure is constant. Here, then, in a adiabatic process, there is no exchange of heat with the surrounding. That means delta Q is equal to 0. The system must be a perfectly insulated system from the surrounding. There is an insulation so that there is no heat exchange with the surrounding. So here the process must be carried out quickly so that there is no sufficient amount of time for the heat to transfer. So the system should not transfer the heat from the surrounding, or the surrounding should not send the heat into the system. So here the temperature, the pressure, and the volume are changing, but the heat is constant. So here an adiabatic process is a process in which the heat is constant. So here the work done is to the change in internal energy. So we have seen that like for example in the other process I've seen that the work done is due to the change in the heat. But here the work done is due to the change in internal energy. Here the work done is due to the change in internal energy, because delta Q is equal to 0. So we have du is equal to delta Q plus dW, and delta Q is equal to 0. That means the work done is due to the change in internal energy. The work done is due to the change in internal energy in a adiabatic process. As you can see, we have the pressure and the volume which are changing. The pressure is decreasing, the volume is the pressure is decreasing, the volume is increasing. The pressure here decreasing, the volume increasing. So the heat stays constant while other parameters are changing. The temperature also and the volume. You can see that the temperature is decreasing while the volume is increasing. So you can also move from B to A where the volume is decreasing and the temperature is increasing. Here also you can move from B to A where we have the volume decreasing and the pressure increasing. But here we have to make sure that the system is at constant, the heat is constant. An example for this adiabatic process, we have a release of air from a pneumatic tire. If you have a pneumatic tire and you are releasing the heat, so there we have a adiabatic process because you are removing the air from the balloon, and there is no exchange of the heat with the surrounding. Another example is the thermos. A good thermos at home is considered as an adiabatic process because there is no heat exchange with the surrounding. You can assume that a good thermos is an adiabatic process. So what it considers is that when you have an adiabatic process, it happens at the delta Q is equal to 0. That means the system does not exchange the heat with the surrounding. So we have also adiabatic expansion and the adiabatic compression. So I told you that the adiabatic process is a process without transfer of heat to or from the system and the delta Q is equal to 0. So during adiabatic expansion, here the gas does work because you have expansion, its temperature decrease. So you are decreasing the temperature and the pressure also is decreased during expansion, but the volume is going to increase during an adiabatic expansion. If we can say, for example, we are expanding, we are increasing the volume, but the pressure and the temperature are going to decrease. You can see the temperature is decreasing while the volume is increasing. The pressure also is decreasing while the volume is increasing because we have an expansion. But that should be at the extent that there is no heat which is extended with the surrounding. So if you can, for example, have the adiabatic expansion with the pressure from here, we have A, where we are decreasing the pressure and increasing the volume during an expansion. We have A to B, and here also we can draw the temperature and the volume where we have the temperature is decreasing and the volume is increasing. So we are in expansion, adiabatic expansion. What does it mean that? So the internal energy is a state function. Internal energy is a state function. That means its value does not depend on the path taken. So the internal energy here does not depend on the path taken from A to B. So you can also use this path and this one. The internal energy in B, because it is a state function, it does not depend where you pass here or you can pass here. It does not depend on the path that is you are taking. So whether you are passing from you are passing here, or whether you are passing here, in that case you get the same internal energy in B. So that means then this internal energy in B, we can get them by using this way. This way then you can get this internal energy coming from A to B by using this way. So from A to B by passing here, we can get the internal energy by passing from A to this point and from this point to B. Now, what is from A to this point? The first phase from A to this point, we have isothermal process. We have the constant temperature. The constant temperature. What is the internal energy? When you have a constant temperature, you have seen that it is 0. Delta T the change in temperature is equal to 0, and internal energy is a function of temperature. In that case, internal energy is 0. That means from A up to here, the internal energy is 0. So now we need to add also from this point to here. From this point to here, we have isochoric process. We have a constant volume. So I have seen that internal energy at constant volume is equal to nCvdT. So then we can say that internal energy is equal to internal energy from isothermal process plus internal energy from isochoric process. And the internal energy from isothermal here is equal to 0, then plus isochoric process, which is equal to nCvdT. And from here you can show that the internal energy for adiabatic extension is also equal to nCvdT, because we asked to show that adiabatic process internal energy is equal to nCvdT. Let's see also in adiabatic compression. So it's a process without transfer of heat to or from the system, because we are compressing. The eta Q is also 0 in compression. So we have adiabatic compression take place quickly. So the process has to take place quickly, so that there is no time for the mixture to exchange heat with the surrounding. So the work done is done on the system. So we are compressing. That means the work done is done on the system. Here the volume is decreasing because we are compressing. The temperature is increasing. During the adiabatic constant compression, we have a volume decreasing, the temperature increasing, but that has to happen at a constant. Adiabatic process happen at constant Q. The eta Q is equal to 0. That means the system does not exchange the heat with the surrounding. So here then we have the temperature, which is, you can see we have a adiabatic process from A to B. So here we are having, when the volume is increasing, we have the expansion. Then for a compression, we need to move from B to A. For compression, we need to move from B to A. So here the volume is decreasing because we are compressing, and the temperature is increasing. So now how to determine the internal energy in point A? Internal energy is a state function. Whether you pass through this way or whether you pass through this way, you get the same internal energy in A. That means from B to this point, so we have an isochoric process, the constant volume. And if from here we have the constant volume, this way. And from this point to A, we have isothermal process. We have a constant temperature isothermal process. Now, what is the internal energy in this point, in this first phase? That means isochoric process. You have seen that internal energy is equal to nCvdT. And isothermal process, the internal energy is equal to 0. So then we need to add them so that we get the internal energy in A. So internal energy is a state function. Its value does not depend on the path taken. So the du in A here, it will be equal to the du in isochoric process here plus the du in isothermal process, and the du in isothermal process here we have 0. So we have du is equal to nCvdT plus 0. Then in adiabatic compression also, the internal energy is equal to nCvdT. So far we have shown that the internal energy for all the process is equal to nCvdT, and for the for internal energy for a constant temperature or isothermal process, we have seen that is equal to 0. For other process, internal energy is equal to nCv.